Hello everyone, how are you all? I hope you are doing very well for your boards. Okay, here I am just to give you one short lecture for coordinate compounds. Okay, many of you find difficulties in these coordinate compounds, but believe me, it's a very simple lesson. Okay, and see what is its weightage? 5 out of 7 with optional 7 marks lesson. Okay, and very easy. So what is there? What are the important questions or what type of questions are asked on this topic? We'll discuss that. Okay. First one is ligand. Ligand, what is meant by ligand? A species which have tendency to donate electron or which is a Lewis base is known as ligand. Okay. Then second point is what are the types of ligands? What are the types of ligands? Different types of ligands are there depending upon number of donating sites, right? So we call these ligands as monodentate ligand. Second one is polydentate ligand, and one more is ambidentate ligand. Monodentate ligand means what? It has only one donating site. Okay, that ligand have more than one atom or more than one atoms, and though they have more than one atoms, only one atom can donate electrons at a time. Means this is NH3, here Cl minus. These are nothing but monodentate ligands. Polydentate ligands means what? As the name suggests, poly, many, dentate, donating site. Many donating sites are there. Many donating sites means how many? So there may be 2, 3 and so on. If there are two donating sites, it's a bidentate ligand. We call it as bidentate ligand, tridentate ligand, and so on. Tetradentate ligand, hexadentate ligand. Okay, EDTA is one example. This bidentate ligand, we have example ethylene diamine. We write it as EN, isn't it? Ethylene diamine is CH2 NH2 CH2 NH2. Polydentate ligand means more than one donating sites are there. Okay, and last one is ambidentate. It has two donating sites, but only one can form bond with central metal ion in the coordinate compound. For example, NO2 or we can write ONO. Similarly, SCN or CNS. Okay, SCN or CNS. These are ambidentate ligands. Even NC and CN, cyanide and isocyanide, this pair is also belongs to ambidentate ligand. Okay, so first point related to ligand and its different types. Next point is what is meant by coordination sphere. So what is coordination sphere? Coordination sphere is the entity enclosed in a square bracket. Coordination sphere is the quantity which is enclosed in a square bracket. That is called as coordination sphere. For example, CO NH3 6 times Cl3. So which is the coordination sphere here? Only this much part, that is CO NH3 6 3 plus. If we ionize this, then obviously this ion will have positive charge. So this is called as coordination sphere. The quantity which is enclosed in a square bracket, that is known as coordination sphere. One more point is there which is known as charge number. Charge number, that is charge on coordinate complex. Okay, very important. Charge number is different and charge number is different and oxidation state of central metal is different. So question is, what is the charge number of this complex? So if I give you example, CONH3 6 Cl3. So what is the charge number of this complex? So charge number of this complex is, what is the charge on the square bracket? Simple. Charge on square bracket is the charge number. Or if we write it as K3FeCN6. So what is the charge number? Charge number is -3. The number at the top of the square bracket. So charge number here -3. And what is oxidation state? Oxidation number, it is related to central metal in that complex. So which is the central metal in this complex? First example, if we consider cobalt, and you have studied rules, how do we find oxidation state? Say oxidation state of cobalt is X and this NH3 is 0, neutral molecule. Chlorine Cl is -1 into 3. So total charge is 0. So we get charge on cobalt equal to +3. So oxidation state of cobalt is +3. If I give you example K4FeCN6. So what is the charge number? Charge number will be, see the difference. I'll calculate both here. Charge number will be equal to -4, right? Charge on this square bracket. If we ionize this, we will get 4K plus and FeCN6 4 minus. So charge number is -4. And what is oxidation number of Fe here? Oxidation number of Fe, K is always +1 into 4 such atoms. Fe we don't know. Cyanide is always -1 into 6. So -6 is equal to 0. So X is equal to +2. So oxidation number of Fe is +2 and charge number is equal to -4. Charge on the complex is the charge number and charge on metal ion is nothing but oxidation number. One more point is there, that is coordination number. Coordination number. What is coordination number of this complex? Like this question is also asked. So coordination number means what? Number of coordinate bonds. Very important. Coordination number means what? Number of coordinate bonds formed by that metal. Coordinate bonds formed by metal. Formed by metal. What does it mean? Formed by central metal in the complex. Formed by central metal in the complex. What does it mean? See, we have one example, CONH3 6 3 plus. Okay, so one cobalt. And how many ligands are there? 6 ligands are there. And we know type of this ligand. It's a monodentate ligand. It means cobalt forms 6 bonds with 6 ammonia. Cobalt forms 6 bonds with 6 ammonia. All are giving electrons to this cobalt. So 6 coordinate bonds are formed. So its coordination number is 6. Okay. If I give you example, COEN thrice plus 3. Now see, in this case, you will say that its coordination number is 3. No, my dear students. Here coordination number is also equal to 6. Why? Because ethylene diamine is bidentate ligand. That's why I did not say number of ligands. I said number of coordinate bonds formed by that central metal. So you should know whether it is bidentate, tridentate or what. And in your syllabus only bidentate ligands are there. One hexadentate is there and that is EDTA. EDTA. Remember this, very important. So CO, ethylene diamine. How do we write? Ethylene diamine, ethylene diamine, ethylene diamine. Isn't it? Ethylene diamine is NH2, CH2, CH2, NH2. Okay, this is the structure. Anyhow, you can write, no problem. And here +3. See how many coordinate bonds are formed by this cobalt? It has formed 6 bonds. So here also its coordination number is 6. You should know little bit of theory. Huh? This is just a review of this summary of this lesson. Next very important point always asked on this topic, that is double salt and coordinate complex. Double salt and coordinate complex. Or what's the difference between double salt and coordinate complex? Okay. So double salt means what? A substance which when dissolved in water dissociates completely into simple ion and loses its identity. Double salt, okay, dissociates into simple ion, dissociates into simple ion and loses its identity in water. Identity, that is known as double salt. You know double salt, that is more salt or kernelite, है ना? More salt more salt, that is FAS. You also call it as FAS, that is FeSO4, NH4 twice SO4 along with 6 water molecules. If we dissociate this, show its dissociation also. If we dissociate this, what do we get? Fe2 plus NH4 plus SO4 2 minus plus water. Don't split that water. H plus OH minus, dissociation is very poor. So we get different ions. Of course, Fe2 plus and FeSO4, they have different properties. So it is said that they lose their identity. So dissociates into simple ions. Dissociates into simple ions. And what is another question asked? That is complex compound or coordinate compound. Example is necessary, huh? Always. It's a 2-mark question. So half mark for this description, half mark for the example. Here also half mark for description, half mark for example. So what is coordinate complex compound or coordinate compound? So which dissociates in water with at least one complex ion. Dissociates, wording is important, dissociates in water with one, at least one complex ion. Means there is complex ion, minimum one complex ion must be there, then it is called as complex compound. And complex ion does not lose its identity in water. Example, CONH36Cl3. If we consider this is a coordinate compound. This is complex, this is counter ion. So CONH3 6 times 3 plus 3 Cl minus. Okay, so this is a complex ion which remains as it is. Properties of this are same. So complex compounds do not lose their identity in aqueous solution. Very important question. Usually it is asked. Next question of coordinate compounds. Next question of coordinate compounds is Werners theory. Give postulates of Werners theory. Once they have asked this question in the board exam, postulates. 4 postulates are there. So 2-mark question. Werners theory. So what are the postulates of Werners theory? Make key points and elaborate those points in your words. Make key points and elaborate these points in your words. So Werners theory. What is it? Number 1. This scientist said that in the complex, metal always have 2 valencies. So primary and secondary valencies. Metals show 2 valencies. CONH36Cl3. So this cobalt have 2 valencies, primary valency and secondary valency. So primary valency is Cl, satisfied by Cl. Secondary valency satisfied by NH3. Don't give example here, just say primary and secondary valency. Second, there are 2 spheres. First point is 2 valencies. Second point is 2 sphere. So these 2 spheres you have to explain in second and third point. So first sphere is primary sphere, or that is also called as ionizable sphere. What is this ionizable sphere? The ions which are separated, which are ionized, are found in ionizable sphere. And this is related to oxidation number. Third one is secondary sphere. Secondary sphere is also called as coordinate sphere. What is coordinate sphere? So coordinate sphere means what? The valency which is not dissociated, or it is related to coordination number, which is tightly held by that central metal. Here it is ionized, can be separated from that metal. This is the main difference. Okay, and one more, 4th postulate, that is secondary valence have fixed arrangement, fixed position, okay, or fixed spatial arrangement, and this results into definite geometry of that compound. Is this clear? Okay, so what are the postulates of Werners theory? Number 1, primary and secondary valence. Every metal have primary and secondary valencies. There are two spheres. First sphere is ionizable sphere, which is related to oxidation number. And what is there in the ionizable sphere? Always anions, negative ions are there. And coordinate sphere, it is the inner sphere. You can say this is outer sphere. Those entities which are outside the square bracket, these are primary valence. Okay, so anions, these are satisfied by anions. Coordination sphere, so here which substances play role of coordinate sphere, which part of coordinate sphere? It is either anion or neutral molecule. Means here there may be ammonia or there may be Cl minus ion possible. Okay, so coordinate sphere includes anions as well as neutral, and this is also known as inner sphere. Inner sphere, these words are not in your book. In old syllabus these words were there, let it be. And the last one, secondary valence have fixed spatial arrangement. Fixed spatial arrangement, therefore that coordinate compound have definite geometry. Okay, after that next point is classification of complexes. We have to classify complexes. So classification of complexes, there are three different methods. Classification of complexes. See, what is this? Classification of complexes. Okay, so depending upon ligands, type of ligand, these are classified into homoleptic and heteroleptic. Homo and hetero, meaning and example. See, it is very easy to score in this lesson. 1 mark question. Homo means same, we all know. So a complex having same type of ligand, that is homo leptic ligand. So example, CO NH3 3 plus, this is homoleptic. Heteroleptic means what? Two different ligands are there. For example, CO NH3 5 times Cl, so this becomes still plus 3. This is 3. Yes, this is minus 2. Cobalt is plus 3. This is minus 1. So charge on this becomes plus 2. So homoleptic means what? Complex having same ligands. Heteroleptic means what? Complex having different ligands. Next type of classification is depending upon charge. Depending upon charge on the complex. Cationic complex. Second one is anionic complex. Cationic, anionic, and third one is neutral complex. Cationic complex, anionic complex, and neutral complex. Name itself indicates the meaning. That complex ion means that square bracket have positive charge. So this is the example. These both are cationic complexes. Any example you can give. CO NH3 3 plus. Anionic means what? FeCN6 4 minus or 3 minus. Both are there. Both exist. Anionic complex. And neutral means what? Neutral means no charge on that complex. No charge on the complex. NiCO4, or you can say CO NH3 3 times Cl3. Just you have to remember examples. Homoleptic, heteroleptic, then depending upon the charge on the complex, cationic, anionic, and neutral complexes. Okay. Next point. Next and very important point is related to its IUPAC nomenclature. Very important, and always question is asked. So 3 marks. 1 year they asked 3 questions on IUPAC nomenclature. 3 mark question it was. So how to give name to that complex? So IUPAC nomenclature. So what is the rule to give IUPAC name? See the format. What is the format? We have to write name of ligand in the beginning. Okay, name of ligand. Then name of metal. Then in bracket we have to write oxidation number of that metal in Roman. That's very important. Not number as 1, 2, 3, 4. Roman letter we have to write. So oxidation number in Roman, and at the end the counter ion. If it is there, that negative ion. Okay. This is the sequence. Mostly we follow this. Okay. If it is if it is cation or anion, then at end you have to write ion. If it is anion, then that metal is written as metallate. Remember these certain rules. In your textbook, page number 196. Page number 196. Yes. See that table. Very, very important. If you see that table, IUPAC nomenclature will be perfect. Okay. See. So ligand. I'll tell you one example. Example is again same. CONH3 6Cl3. So what is the sequence? First name of ligand. Ligand is ammonia. Ammonia, name for this ammonia is amine. See the spelling, double M is important here. It's a neutral. Neutral ligand have special name like amine, A double M, I-N-E. If it is water, it is aqua. If it is CO, it is carbonyl group. Okay. And if it is negative ion, then it ends with O, like Cl minus, so chloro. Okay, and so on. You just refer that table. So what it will be? IUPAC name of this compound would be, how many ligands are there? You can say number of ligands first. Number of ligands. Those prefixes we have to use. So how many ligands are there? 6. So hexa. Then ligand, name of ligand. Amine, hexa, amine. Then metal. This is positively charged complex. We know. It is written first. If square bracket is first, then it is positive. If square bracket is afterwards, see, square bracket is afterwards, then it is negative. Got it? Very simple to identify whether it is positive or negative. If something is there after square bracket, means this is positive. If something is there before square bracket, means it is negative, anionic complex. Okay. So what will it be? Hexaamine, cobalt. This is positive, means we have to write metal as it is, cobalt. And oxidation number, I told you how do we write oxidation number, that is +3. So this is hexaamine, cobalt, hexaamine, no space, hexaamine, cobalt. Oxidation state is 3 and this is chloride. Got it? Similarly here cyanide, but it's negative ion, so it ends with O. So cyano. What is it? Ferrate. See, we have written it afterwards at the end, means before that some ion is there, so this is at the end. So ferrate, so it becomes ATE. Metal, at the end it becomes ATE, metallate. Copper becomes cuprate, nickel becomes nickelate, Fe becomes ferrate, and so on. Okay. So ferrate, and we have to write its oxidation state. It is +2. Of course, potassium I forgot to write, so that potassium in the beginning. Is this clear? While writing, if more than one ligands are there, then we have to follow alphabetical order of that ligand. One more important point, prefixes we use. If that ligand have number in its name, like ethylene diamine, diamine is there, na? Diamine is there. So ethylene diamine. Okay. So for such ligand, we have to use prefix as bis, tris, and so on. Getting my point? For example, COEN thrice. So how do we name it? How many ethylene diamine are there? 3. So if it is without number name, we simply call it as tri. But its name has a number. So if ligand's name has number, then that prefix changes to bis, tris, tetrakis, and so on. Okay. So here 3 ligands are there. So this becomes tris. Then in bracket you have to write its name. Tris ethylene diamine. Here not double M. Tris ethylene diamine. Close the bracket. Then cobalt in bracket 3 iron. There is no counter ion at the end. So here there will be iron. Clear? So just refer that page 196. Your doubts will be clear. Next and very important point, that is EAN, effective atomic number. Always question is there. EAN, EAN. What is EAN? What is EAN? You all know, effective atomic number. Effective atomic number. So effective atomic number. Question is, what is effective atomic number and what is EAN rule, and calculate. 3 questions I told you. 1. What is effective atomic number? Effective atomic number means number of electrons around the central metal atom in a complex is called as EAN. What is EAN? Number of electrons around the central metal atom in the complex is called as EAN. What is EAN rule? What is EAN rule? Rule is that central metal goes on accepting electrons till its configuration becomes like next inert gas. Like, okay, so metal continues accepting electrons till its configuration becomes next inert gas. Next inert gas, till its configuration becomes like next inert gas. For example, FeCN6 4 minus. Okay, this is the compound, and they asked us to find EAN of Fe. So what is the rule? What is the formula? EAN is equal to Z minus X plus Y. You all know the terms. Z means atomic number, X means charge on metal, and Y means number of electrons accepted from ligand. So Z of Fe 26 minus, what is charge on Fe? X minus 6 is minus 4, X is equal to plus 2. So minus that charge, minus 2, plus how many electrons are gained from ligand? One ligand gives 2 electrons. One ligand gives 2 electrons. It's a Lewis base. So electron pair donor, it gives 2 electrons. So 2 into 6. 2 into 6. See, this is 24 plus 6. How many? 12 is equal to 36. And 36 is nothing but krypton. There are few compounds where that EAN rule is not followed, but always question is there, calculate EAN for this atom, this metal ion in the complex. Clear this point? EAN. What is EAN? Number of electrons around central metal. What is EAN rule? Metal continues accepting electrons till its configuration becomes like next inert gas. Like next inert gas. Example, and question is, find EAN of metal in this complex. And how to find? EAN is equal to Z minus X plus Y. Okay. Next point. Next and very important point is on the basis of isomers. In MCQs also many questions are there depending upon isomers. One tabular form I'll give here. So your all doubts related to isomers will be clear. See, isomers. Two types of isomers are there. One is stereoisomer and other one is structural isomers. Stereoisomers means different spatial arrangement. Two are there which show stereoisomers. One is cis and trans. So we call them as geometrical isomers, and other one is optical isomers. Cis and trans. And here optical means D and L isomers. There are two compounds, two coordinate complexes which show geometrical isomers. One having coordination number 4 and other having coordination number 6. Here it is shown by only coordination number 6. And 4 also square planar, not tetrahedral. They don't show geometrical isomers. Okay. So coordination number is 4. So example of this. See, MA2B2. Suppose this A and B are ligands. So how do we get MA2B2? AA on the same side. AA on the same side of the metals. and anyhow you can write here 2A 2B here, no problem. Okay, so AA on the same side, BB on the same side, cis, and MAA on the opposite side, BB opposite side, so trans. Cis and trans is possible here. And one more they have given, MA2BC, MA2BC. Okay, so just change one ligand, say here Cl. Okay, C, here also we put C. So focus on these two groups. These are on the same side, cis. Similar groups are on the opposite side, that is trans. Clear? Now coordination number is 6. So there are 3 such compounds, MA4B2. Second one is MA4BC. And third one is MAA2B2. What does it mean? What does it mean? See, you can take any example or simply write general form. No problem. Okay. So, first one, that is MA4B2. Coordination number 6 means octahedral geometry. Octahedral geometry. So, like this. Here A, and 2B. So, all are at adjacent position. Focus on this 2B. Two different. 2 ligands which are different than rest. So 2 on the adjacent position, this is cis, and if we write this 2 on, see, opposite side or diagonally placed, when these 2B are diagonally placed, it becomes trans. Here A. Got it? Similarly, A4BC, so we have to keep 4A as it is. B and C, we have to change. So replace one B by C. Replace one B by C. So here C. So these are on the opposite side. So this is trans, and these are on the same side. So it is cis. And one more is there, AA2. A is enclosed in bracket. It means it's a bidentate ligand. So let us consider bidentate ligand means these two can combine with each other in this way. In this way, right? This also connected to this each other in this way. So this is A and A. Here also A and A. And other one is B2. Here also B. See, these two are on the same side. Right? These two B are adjacent. These two groups are adjacent. Cis form. Here B. Here B. Here these two A are connected in this way. So this is in the trans form. So AA2, B2, cis form, trans form. Is this clear? Now optical isomers. Optical isomers are shown by this cyclic compounds. Okay? Cyclic compounds. How is it? See. So here also they have given us 2 types. One is MAA3. MAA3. And other one is MAA2B2. MAA3 means what? See, metal. Okay, this is AA, right? And its mirror image. Optical isomers means what? Non-identical mirror images, isn't it? Non-superimposable mirror images. Non-superimposable mirror images. See, this is the mirror image, cis form, mirror image. And if we say it's trans form, so trans form, no trans is possible in this case. Here it is possible, but that is not active. Okay. So D and L. One is called as D, other is called as L. See what happens in this case. Central metal attached to 2 AA. So this is one AA, another AA, and 2B. So here B and B. See, this is the mirror. You have to name it properly. Yeah? This is the mirror. Then here also M. This is B. This is one ligand and this is another bidentate ligand. Got it? So these two are cis form. This is cis form. I told you this can show cis as well as trans. But its trans is optically inactive. What will be its trans form? See, I will draw here. Trans form. M. Trans means same groups are on the opposite side. Right? Like this. And see its mirror image. Mirror image is superimposable. Superimposable mirror images, if we keep it on this, they exactly match. So superimposable mirror images are not optically active. So its Cis form is only optically active. Trans form is optically inactive. Clear? These are all stereoisomers. And what are geometrical structural isomers? So there are 4 structural isomers. One is linkage isomer. Second one is coordinate isomer. Third one is hydrate isomer. And one more is there, that is ionization isomer. And fourth one is, what is it? Solvate, or it is also called as hydrate isomer. Solvate or hydrate, related to solvent, water. So linkage, name itself indicates the meaning. Linkage is different, means this is the hint which is linkage isomer, where ambidentate ligand is involved, that is linkage. Ambidentate ligand, if we find ambidentate ligand there, then it is linkage. Means what? CO NO2 whatever 6 times, and another one if I write CO ONO 6 times. See, here nitrogen is attached to cobalt, here oxygen is attached to cobalt, means ambidentate ligand. If ambidentate ligand is there, then it is linkage. Second one is coordinate. Coordinate, what's the hint to identify coordinate? Coordinate means cation and anion both must be, cation as well as anion must be complexes. Okay, if we consider here CONH3 so this is cation, right? This is 3 plus, and we balance the charge by putting there Cl3. Okay, but what they are saying, that here another counter ion should also be complex. So see, Cr will have here -3 charge and this will have +3 charge. So coordinate means what? Both should be complexes, cation and anion. And how do we get coordinate complex? Just interchange their ligands. This is one, and what is its example? Cr NH3 6 times CO Cl6. Okay, this is an example of this coordinate complex. So what is important? Both ions must be coordinate. Okay, ionization isomers. Ionization isomer means what? Different ions are obtained after ionization, isn't it? CO NH3 5 times Cl and Br, and take Br inside and Cl outside. Very simple. You don't have to remember examples. Just understand the meaning. Okay, Cl is outside. If we ionize this, we'll get Br minus. This one ion and Br minus. If we ionize this, we'll get this and Cl minus. So different ions are obtained. These are ionization isomer. And solvate isomer means what? If we see water in that complex acting as ligand as well as water outside that square bracket, then it is solvate isomer. Means what? Cr H2O6 Cl3 and Cr H2O 5 times Cl and one Cl2 here and one H2O is outside. So this is called as solvate or hydrate isomer. Is this clear? I hope this summary is enough for you to identify the type of isomer. Mostly MCQ is asked which type of isomer is this, or how many isomers are possible, like these questions are asked on this topic. Okay, next point is stability of the complex. Stability of the complex, how do we find stability of the complex? So charge to radius ratio should be higher, means complex is stable, and another, that ligand should be strong. Strong ligand means complex is stable. Strong ligand means complex is stable. Okay, after that VBT, where to see application of VBT. So sometimes they say explain formation of CONH3 3 plus, and I always tell you, see, this is CO is 27, it is in +3, so CO +3 configuration becomes argon 4s0 3d6. This is 4s2, of course argon 4s2 3d7 loses 3 electrons. So 2 electrons from 4s, 1 electron from 3d. So 4s0 3d6. See its configuration, it becomes like this, right? Yes. Now ligand coming towards this cobalt is NH3, and we know NH3 is strong ligand. So strong ligand causes not back bonding, it causes pairing. So 6 electrons we can show like this, right? When ammonia comes, this electron goes and pairs up here, even this electron goes here. So what do we get? D2sp3 hybridization. So inner complex is used, inner orbital is used, so its hybridization is D2sp3. And low spin, this is also called as low spin. Why? Because number of unpaired electrons are less. Spin means unpaired electrons. Less number of unpaired electrons, so it is low spin. Similarly, see another example, COF6 3 minus. So CO is again plus 3. Now fluorine coming towards this is a weak ligand. So again configuration will become like this. 1, 2, 3, 4, 5, 6. Now fluorine is weak. So because of weak ligand, pairing does not happen. So what that fluorine has to do? It has to use d orbital of next shell. So sp3 d2. This is 4s, 4p, 4d. In the previous case 3d, 4s and 4p. So d of the inner shell. So we wrote d first. Here d of the outer shell. So its configuration become sp3. sp3. So sp3 d2, sp3 d2, and this is called as high spin complex. Why? Number of unpaired electrons are more here. 4 unpaired electrons are there. So this is example of high spin complex. Similarly, 2 more are given. One is NiCl4 and other one is NiCN4. You can do it in the same way. NiCl4 2 minus and NiCN4 CN4 2 minus. See, Cl4 Ni is 28. 28 means argon. 4s2 3d8. Charge on Ni is plus 2. It loses 2 electrons, means it is argon. 4s0 3d8. So 3d8 means how do we write? See, 1 2 3 4 5 6 7 and 8. S is empty and here this p orbital. Now we want 4 empty orbital. Chlorine is weak ligand, so pairing is not possible. So this undergoes sp3 hybridization. Clear? So this NiCl4 2 minus is sp3 hybridized. And what about this? NiCl4 2 minus. Cyanide is strong ligand, so it causes pairing. This electron goes back and get paired up. So one orbital becomes vacant here. So it is used in the hybridization. So this becomes dsp2 hybridization. dsp2 hybridization, square planar. Many times they ask us what is its magnetic behavior. If unpaired electron is there, it's paramagnetic. If no unpaired electron, it is diamagnetic. So this is diamagnetic, this is paramagnetic. Like these questions are also asked. And the last point is applications of these coordinate complexes. What are the applications? In MCQs they ask biological applications. Biological applications means hemoglobin. Hemoglobin contains Fe. What is its oxidation state? Like this question is also asked in MCQs. So always Fe is in +2 oxidation state in hemoglobin. Then chlorophyll has Mg2 plus complex in chlorophyll. Then one more is there, that is cobalt B12. It is found in vitamin B12. Vitamin B12 contains cobalt as central metal. Okay. Second one is in medicines. One more question. Explain medicinal applications of complexes. So in medicine, cisplatin. It is used in cancer treatment, and if it is lead poisoning, then EDTA is used. One more is EDTA, use of EDTA, that is making hard water soft. So like this question is also possible. Give 2 applications of EDTA. in the complexes, right? One, lead poisoning, to prevent lead poisoning, and second one is making hard water soft. Okay, and last one in electroplating. Whenever any object were to coat with silver metal or gold metal, then we use complexes like argentocyanide, right? So AgCN twice, KAgCN twice, or KAuCN twice. Like this, substances are used as electrolyte for the coating for electroplating. Okay, that's all coordinate compounds. If you have any doubt, you can put in this comment box. I will answer if you have any doubt related to this. Okay, chalo, all the best, good luck.